video begins the series on what is a well-posed predictive control problem. First then, let's review chapters 1 and 2. The first two chapters introduced concepts of prediction, optimization and implementation and showed that these made good intuitive sense if you're designing a control law. Some specific MPC algorithms were defined. In fact, what we did is we gave largely the GPC algorithm and we focused on the constraint-free case. However, the early chapters did not engage in discussions on whether the proposed algorithms resulted in good closed-loop performance or not. And we did not look at how might you choose the horizons, the output horizon and the input horizon, or how you might choose the weights. Some core questions then. Are there good and bad choices for the input and output horizons? Are there good and bad choices for the weights in the performance index? And is the fundamental design of GPC/DMC, is it sensible or not? Or are there some major theoretical flaws within it? Conceptually it makes sense, but if we analyse it in more detail, are there flaws that we hadn't expected? Now here's the key point. It's easy to show, and that's what we're going to do here, that poor choices of horizons can lead to very poor behaviour. So there are indeed some theoretical flaws if you are not careful. Just as a by-the-by, we're not going to look at constraints in this particular chapter because that will confuse the issues, and we'll deal with that in a later chapter. Illustrations of poor behaviour then. We're going to use MATLAB to show how deploying a GPC on its own, even in the constraint-free case, no disturbances and no noise, there is still no guarantee of good behaviour. So you've got a conceptually sensible algorithm, something you said intuitively, this makes sense, it's based upon what humans do, and yet it might still give stupid or poor answers. And the key thing is, poor choices of horizons can result in what are supposedly optimal strategies because they come from an optimization that in fact are far from optimal. And this is why. What you've done is you've made an arbitrary choice of a performance index, and you've also made an arbitrary choice of the degrees of freedom. And because I've put the word arbitrary in there, then optimizing an arbitrary performance doesn't necessarily mean that you will be optimal. We've got some files here which you can get from the server on the Google sites if you want, just to look at how this works. First example then, you'll see here I've chosen an output horizon of 15, an input horizon of 1, a weighting of 0.1, and I've calculated the control law, and this is how it's behaved. And clearly this output is not behaving particularly well, and neither is the input. So we've not got good performance out of this system. Now what I can do is use the same model and change the output horizon. So here I've now made the output horizon 3. Are you happy with this output trajectory? And again you'll see it's very different from the previous one because I've changed the output horizon, but it's still pretty poor. So that's two simple examples of I've used a GPC algorithm, I've put in some horizons, and it's simply not worked. Here's a different system. Would you be happy with a response like this? And most people would probably argue that this is a little bit too oscillatory, the overshoot's a little bit too big. You'll notice I've used different horizons here, 6 and 1, compared to the other examples, but it's not working. Here's another example. I've chosen here horizons of 3 and 1, but what you can see in this particular case is GPC has totally failed. The closed loop is unstable. However, if I take the same model and change ny, so in this particular case you'll see now I've changed ny from 3 to 6, I've now got reasonably nice behaviour. So here's the question. Why does GPC work well for some choices and not well for others? Is there some underpinning explanation which would enable us to do systematic design? And it's noted that intuitively, if GPC is poor in the unconstrained case, which is what we're doing in this chapter, then we're not going to expect it to do well when we start introducing constraints. The other thing we're going to do is we're focusing here on single input, single output problems, because if we can show that there are a number of issues with single input, single output problems, then the same issues are clearly going to carry across to the multivariable case, and it's a lot easier to see these issues in the CISO case. Now, this is a bit of historical information. Early on, in the 80s and the 90s, authors tried to find some mathematical relationships between stability performance and the choice of horizons. I wouldn't say that they got particularly far, and the key thing to note is that approach is largely considered invalid nowadays. Okay, there's other ways of dealing with it, and why that's so will probably become apparent as you go through this chapter. What's a well-posed optimization then? Rather than going straight to the well-known solution, which will come in later chapters, in these videos we're going to begin by trying to understand the MPC optimization, or in particular we're focusing on the sort of performance indices you see in GPC. A good understanding will allow the user to always deploy sensible choices. If you understand how the optimization works and what's going on, then you're not likely to misuse it. It will also give you good insight into the normal recommendations in the literature, which will be covered in later chapters. Questions you might want to consider then are: how should we choose the input and output horizons, how and why? And also, is there some link between those and the weightings? I'm going to give an analogy that helps you understand where we're going. So here's the analogy. You need to get from a point A, there's point A up here, to a point B down here, and you're going to use a GPC type of algorithm which says I'm going to give myself a control horizon of 2, or here what I'm saying is I can choose to change direction twice. My initial direction is one choice and then a change later on. So the step 1 is saying, using at most 2 turns, optimize your route to B, take the first turn and move, let's say, for a minute. So this is what's going to happen. You'll see there's my initial direction, which I follow until I get to a point there, and then I turn once and I get to B. So that's an example of an optimization that might come out of a GPC algorithm. But I'm only going to move for a minute, so I'm going to get to this point here. And when I get to that point there, what I'm going to do is say, okay, you can now re-optimize. So what you can do now is you can say, from this new point, optimize the trajectory to get you to B, again allowing yourself 2 turns. Now what could easily happen here is you come up with a solution like this. And what do you notice? You've taken a totally different route to the route that you originally planned. You will then move along and get to this point here, and then again you will re-optimize. Now I've not put it in. If you were to re-optimize at this point, you might end up doing something like this. And the key thing is you will see you keep changing your mind. So you'd planned what was supposedly an optimum route, you move a bit and you say, oh, that wasn't actually optimum, I've now found a better route. And you move along and you say, oh, that wasn't an optimum, I've now found a better route. So in other words, what you thought was optimum at the first sample was far from it. And here's a key question then. What if I'd allowed myself more turns in my planning at the outset? Then I would have probably ended up with a route a bit like this green one, which you can see is far, far shorter. So what does this tell you? The optimization at the first step was what I call ill-posed, or you can use the word foolish as you like, as you were unable to get close to the trajectory you really wanted. The trajectory you really wanted is this green one. It's obviously much shorter. So that's example 1, where you've got a problem. You were unable to get close to the real optimum, to choose the best route. So we hadn't included the best route in the class of possible predictions because we needed more turns. But the other thing, which is key, is we kept changing our mind. And because we kept changing our mind, it meant that the optimization that we did was clearly not sensible. And therefore, you get this summary at the bottom. Just because I use an optimization does not mean the result is optimal, because the critical thing is I might be solving, I've used the word stupid, a stupid optimization. I've set myself an optimization which really does not make sense. Some key insights then. What is a well-posed optimization? The optimization of J is only meaningful if the optimized trajectories are close to the closed-loop responses that result. In other words, we cannot keep changing our mind. If we keep changing our mind, then the optimum we thought at this sample clearly wasn't optimum at all, because I've gone one sample later and said, oh, that was wrong, I'm going to do something different. So the optimized trajectories must be close to the final trajectory we actually follow. If the optimized predictions differ significantly from the resulting closed-loop behavior, then the predictions are, I'm going to use the word meaningless, and thus the optimization is meaningless, as they do not represent what is actually going to happen. What if the predictions are also not close to what we really want? So if you were to do a global optimization, you would say, here's the global optimum. And clearly, if the optimization can't get close to that, then it's also, in some sense, meaningless. So the desired behavior must be in the class of predictions over which we optimize. And you'll notice critically here, these are two similar but different points. Examples will show that if there is a close match between, and here's the key word, the predictions, the desired behavior, and the closed-loop behavior, and we can make that happen if and only if some specific conditions are met. And if this doesn't happen, then your horizons are not well chosen. As an aside, just to remind you, we're not in these videos going to deal with feed-forward. We're going to assume that the target is a constant, and there's no advanced knowledge of that. And the reason for doing that is, again, if you start introducing feed-forward, it introduces other concepts which will confuse what we're trying to communicate in this particular chapter.